Okay. In this video, I'll be starting off with the last module, second chapter, that is uniform plane waves. Okay. So before I start with any derivation in this, just an introduction. Okay, just do an introduction about what is a plane wave. Okay. So as you all know, wave is nothing but it is a means through which information can be transferred from one place to the other place. Right? It either carries a information in terms of energy, and that energy can be either an electric field or a magnetic field. If it combines both the types of fields, that is both electrical and magnetic, then we call such waves as electromagnetic waves. And both this electric and magnetic fields will always be at right angles to each other. They'll be at 90-degree to each other. So we call them as transverse electromagnetic wave, or in short, TEM waves. Okay. So here, the first part of this is going to be the general wave equations. Now, as I told you, wave is nothing but a means through which carries some energy or information in it, and it needs to be transferred from source to destination. And how do we mathematically represent this? What is the equation that can be used to represent a electromagnetic wave? That is what we're going to see in the first part. So here I'm going to do some derivation on trying to find out what is the mathematical representation of a wave, that is electromagnetic wave. Okay. So this is going to be the general wave equation. And here in this, we are going to get the equations in terms of four parameters. First one is electric field intensity E. Second is electric flux density D. Third is magnetic field intensity H. And fourth, magnetic flux density B. Okay, so you will be finding equations in four parameters: E, D, H, and B. So we'll start with the derivation now. We are doing some assumptions here. We have assumed that we have a linear homogeneous, that is, it's going to be an equipotential, or it is going to be a uh, region where you have constant parameter, and then isotropic medium with parameters mu, epsilon, and sigma. Mu is permeability, epsilon permittivity, and sigma is conductivity. And we also know that the Ohm's law, that is J equal to sigma into E, applies to this system, and we have a charge-free region. Okay, and one of the very important thing to remember here is we say that the electromagnetic wave exists only if it satisfies all the four Maxwell's equation throughout its traveling region. That is, starting from the source till the destination and through the medium through which it is traveling. Every point of time, it needs to satisfy all the four Maxwell's equation. Only then we say that it is an electromagnetic wave and it is existing in nature. Okay, so that's why in the derivation, we are going to start off with considering the four Maxwell's equation. Okay, so the first equation is del cross E, which is minus mu dou H by dou T. We have seen these equations just in the first chapter of module 5. So we have to just make a note of these equations again, and we'll be using these to derive the mathematical equation of the uniform plane wave. Okay, so remember these four equations. Del cross E is equal to minus mu dou H by dou T. Del cross H is conduction current density sigma E, and displacement current density epsilon dou E by dou T. It's actually dou D by dou T. D can written as epsilon into E. That's how we got this part. Okay. And the third one is del dot B is equal to 0, or del dot H equal to 0. Fourth is del dot D is equal to 0, or del dot E is equal to 0. So we are now going to start off by considering the first equation here. We'll take the help of first equation and get the other representations. So we have considered first one, del cross E is equal to mu into dou H by dou T. Okay, minus mu into dou H by dou T. And what they have done for the first equation is they are taking curl on both the sides of this equation. Okay, so it becomes del cross E, which is equal to mu is a constant which can be kept outside. You will be getting del cross dou H by dou T. Again, this del cross and dou by dou T can be interchanged and written. So the next line you see, it becomes minus mu dou by dou T of del cross H. The del cross is taken inside the differentiation term. Okay. And now in this equation, in place of del cross H, you can substitute the second Maxwell's form, that is this one. In place of del cross H, you can put sigma into E plus epsilon into dou E by dou T. So that substitution is done here. And then open bracket and multiply this. This open bracket here, multiply, you will get minus sigma mu sigma dou E by dou T, minus into plus minus mu into epsilon, dou by dou T into dou E by dou T becomes dou square E by dou T square, double differentiation. Okay. And on the left hand side, we are using the vector identity. You have seen this equation even before. If you are taking double curl, that is del cross E, then it can be written as del of del dot E, divergence, minus del square E. Okay. So this is the vector identity you need to remember. So I'm going to replace this left hand side with this equation. And now if you see the fourth Maxwell's equation, the divergence of E is said to be 0. So if I use that property here, this portion of the equation becomes 0. So I'll be left only with minus del square E. So finally I'll be getting the equation as minus del square E is equal to minus mu sigma dou E by dou T minus mu epsilon dou square E by dou T square. And if I remove the minus from both the sides, I will be getting the final solution here, that is del square E is equal to Laplace of E is equal to, first term will be mu into sigma, single differentiation of E, plus second term is mu into epsilon, double differentiation of E. Okay, so this is the equation you are getting for the wave, electromagnetic wave in terms of E. Okay, so del square E is equal to mu into sigma, single differentiation, plus mu into epsilon, double differentiation. Now in the same equation, if I want to replace it by D, I just have to multiply epsilon on both the sides. That is what is done here. If I multiply both the sides by epsilon, epsilon into E becomes D. Here again, epsilon into E becomes D. Epsilon into E is D. Right? So you compare the two equations. None of the other parameters are changing. What is changing is only instead of E, you are writing D here. Okay. So this is the first equation is called the wave equation for electric field. This is wave equation in terms of electric flux density. Okay. So mu sigma, mu epsilon or del square, nothing is changing. Only change that happens here is instead of E, you will be having D. Okay, so to derive these two equations, we started with the first Maxwell's equation del cross E. We took curl on both the sides. Okay, and then we got del cross H and we substituted the second Maxwell's equation in place of del cross H here. Open bracket and multiply, use the vector identity and use the again fourth Maxwell's equation called del dot E equal to 0. And finally, you will be getting this expression. And in the same equation, if I multiply throughout by epsilon, the E becomes D. So these are the first two wave equations in terms of electric field intensity E and electric flux density D. So same thing you need to do for magnetic field also. For that case, we will be starting with the second equation. The starting equation is going to be the second one now. That is del cross H. Okay. So if you see, for the second part, we are going with del cross H. And we are going to take curl on both the sides of this equation. Okay, so curl on both the sides. Here, sigma is a constant which can be kept outside. You'll get del cross E plus epsilon can be kept outside, and dou by dou T and del cross can be interchanged. So it becomes dou by dou T of del cross E. And now in place of del cross E, substitute the first Maxwell's equation which you had listed out initially. Right? So put this here in place of del cross E. So you got this. Okay, so now you have the equation. Again, I'm going to use the vector identity for left hand side. That will become del of del dot H minus del square H. And again, we know from the listed equation, del dot H is said to be 0. So which makes this value 0 and only this will be left. Right? And if I substitute that, finally I'll get the equation, third equation, that is del square H equal to mu sigma dou H by dou T plus mu epsilon dou square H by dou T square. There is no difference if you compare this equation with the remaining two. You see there is no difference in any other values. Only thing that changes is instead of E or D, you have H here. Okay. And now to this equation, if I multiply throughout by mu into H becomes D. And that is how you get the fourth equation. Del square B is equal to mu sigma dou B by dou T plus mu epsilon dou square B by dou T square. Okay, so these are the four equations of the wave. This is how mathematically you can represent the electromagnetic waves. Okay, so in general, if I have to show all the four, del square doesn't change. Only the parameter changes. E, D, H or B. You can choose anyone according to the value that is given. On the right hand side, mu sigma dou by dou t is constant. Only these parameters change. Plus mu epsilon dou square by dou t square. And again only these parameters change. So if I write in terms of E, it becomes del square E is equal to mu sigma dou E by dou t plus mu epsilon dou square E by dou t square. If I want in terms of D, it will become del square D mu sigma dou D by dou T mu epsilon dou square D by dou T square. Similarly, you will get for H and B. So total four equations for wave. Okay. So this is the general representation, general mathematical representation of electromagnetic waves in terms of the four parameters. Electric field intensity E, electric flux density D, magnetic field intensity H, and magnetic flux density B. Okay. So now in the next coming topics, what we're going to do is we will see what are the modifications that needs to be done to these general equations based upon the medium in which these waves are traveling. The wave can be traveling in a free space, or it can be in a dielectric medium, or it can be in a conductor. So based on the type of medium, there will be some changes happening in the parameters. And because of that, there is going to be a changes happening in the equations also, representation. Okay. So we'll see that in the next videos. Thank you.